Welcome to module 7 of database management systems course in IIT Madras BSc online program. In the last module, we have got started to talk about specific details of relational model. In that, we introduced the basic notions of attributes, their types, relational schema and instance, and keys and their categorization. And we just talked about a glimpse of the languages that relational system will have. We will continue on that in this module, and we will try to understand the relational algebra, the first language for handling query in greater depth. Particularly, we talk about its operators in detail. So, these are the list of operators that we will specifically discuss one by one. So, let us get started. So, we talk about relational operators. Now, before I start talking of the operators, I would like to remind you of something that I have already mentioned earlier, is that remember always that a relation is a set. So, the ordering of elements or the ordering of rows and tuples in a relation is inconsequential. I can order them in whatever way I want. So, if you look at the relation on left having two attributes a b and 4 different tuples a 1 b 1, a 1 b 2, a 2 b 1, a 2 b 2. On the right, you have them ordered in a different way, but it is the same set. So, they are same. These relations are same. These instances are equivalent, these instances are identical. Second, a set must always have its elements as unique. So, all rows and tuples must be distinct. So, on left, I have a relational instance where a 1 b 1 is duplicated, so is a 1 b 2. These are not allowed. So, only one of those will have to be there. So, what we show on right, a 1 b 1 and a 1 b 2 is the correct relation, the left one is a wrong relation, it will never exist. Right? So, keep these two in mind as we discuss the operators. These principles will regularly, periodically come into effect. So, we talk on different operators. First is called the select, and as the name suggests, select operation is to select a subset of rows from a relational instance which satisfy a particular condition. Okay. So, if you look at the select is written in terms of this notation, Greek sigma. And then it has as a subscript a Boolean condition, which is a condition that every tuple being selected from the original relational instance must satisfy, and this is the name of the relational instance. So, this is your select is. So, what does it say? It says A equal to B. This is the original relation R. That is, I will take only those tuples where A is equal to B, that is the first part of the condition, and then say and D greater than 5. So, even within that, I will take only those where D is greater than 5. So, let us say let us try A equal to B. So, these two will have to be identical. So, this is a candidate, this is a candidate, this is a candidate, this is crossed out because alpha beta A is not equal to B. So, out of these three that we have got from A equal to B, since I have a conjunction, since I have and, I have to check if D is greater than 5. D is greater than 5, D is not greater than 5, cancelled out, D is greater than 5. So, finally, I am left with two tuples, this and this. which is my selection result. What would have happened if instead of this, if I would have OR, instead of this if I would have OR, then if I have A equal to B or D greater than 5. A equal to B will take this, take this, take this. B D greater than 5 will take this and take this, and it is OR, any one of them condition have to satisfy. So, if I do a select of A equal to B or D greater than 5 of R, then I will get the whole R itself. That is possible, but here it is AND, so I got a smaller relation. So, that is a selection is a very important thing. You can select one specific tuple out, or you can take a set of tuples out. Let us go to the next operation. The next operation is called projection. That is, a selection was taking out few rows horizontally. Projection will take out some columns, and if you take out a column, you take out the column as a whole. So, projection is written in terms of pi here, and you list the columns that you want to project out, that you want to keep. Anything that you do not write here is taken out, and then the original relational schema. So, you have A, B, C, and you are doing projection on A, C. So, this B will be simply erased out. If you erase out B, then this is what you get: alpha 1, beta 1, beta 2. Now, remember that principle, that every row in a relation has to be unique. So, I cannot have entries like this. So, one of them will get deleted, and what I get is this relation. Okay. What will happen if I do pi A B R? Say pi A B of R, what do I get? This is gone. Now, I will get this, and you can see that all of them incidentally are unique. So, there will be no removal of row that will happen. What will be pi A of R? Only alpha and beta. So, it is A right. So, that is the basic principle of projection. So, we know horizontal cuts, we know vertical cuts. Let us go to the next one. This is more classical set theory operation, that is union. So, if two relations have identical set of attributes, then you can take their relation, take their union. I mean, obviously, if this is A B, attribute A B, and that is attribute C D, you cannot do a union, A B and A B. If you do a union, what will happen? Then all tuples, it is just that after this table you put the rest, and then unicify. Unification is required, because here if you do union, you will find that this and this will come twice, because you are putting them together. So, you will have to unicify and have it only once. This is your union, very simple. Next is difference. This is a difference, right? I have a set R, I have a set S. So, this is my, what is difference? Difference is what are there, what is there in R, but not in S, right. So, you take out those things in S which are already in R. So, this is there, this is there. So, you have to take out this element. this row, and you are left with. So, it is basically, you can say that if you have if you take the intersection of R and S and remove that from R, then you have R minus S, right? Simple. But this again is set theoretic. Other than select and project that we have seen so far, the other two, union and set difference, are simple set operations. Now, you have intersection as well, tuples which are common to both. Now, intersection and difference are not independent, because we know that one can be written in terms of the other. So, if you have difference, even without the intersection operator, you have the intersection, because it is this, very easy to see. So, it is R minus S is this is R, this is S. Now, if you do R minus S, that is from R, if you take this out, then what will be left is this part, which is the intersection, right. So, that is simple set algebra. Then you have Cartesian product, again a set operation, that is, take the columns of this, take the columns of this, make all possible combinations. So, you have 2 tuples here, you have 4 tuples here. So, you have 2 cross 4 is 8 tuples, you will get 1, 2, 3, 4, 5, 6, 7, 8. So, if you really see that all possible pairing of the tuples in table 1 and table 2 are present in the result, which is the Cartesian product of the two relations, right. And it is easy to see that if you take a Cartesian product, then you can get back. How do you get back the relation, original relation? So, I can say that R is equal to, if I take Cartesian product of R and S, and or rather I will write it as capital R to mean that is a relational schema of R. So, if I take the Cartesian product and again project it on A B, I will get back the relation R. Similarly, for S, S is mind you, I mean I am using capital here to mean that R basically is A B, S basically is C D E. Those are the schema, because what we have in R and S lowercase are basically the instances, right. So, this is the Cartesian product, which was a set. Now, you get into little nuances, because suppose between the two relations that you want to do Cartesian product with, suppose there is a column, one or more columns which have the same name. Now, in the result relation, you cannot have this, because you cannot have two attributes by the same name. So, what is done is very simple, you just uniquify the name. How do you uniquify? You make this B as R dot B and make this B as S dot B. Okay. So, when you see that between the two relations there is one or more attribute which are identical, then you just qualify the name of that attribute with the name of the relation, because R and S are different. So, their names are different. So, R dot B and S dot B are different, and then you do the normal Cartesian product. So, only thing is you will have a different set of names. You will still have 5 attributes, but you will have different names for them. So, this is kind of a little bit additional trick that you need for the relational algebra, which you do not need in the set theory, because in set theory you do not talk about unification of attribute names. Now, as you do that, 2 things. One is how do you change this name is one question. Other is maybe you have done this R dot B and S dot B and you are not happy, you want to call R dot B as say P and S dot B as Q. So, how do you rename something? So, what you can say is you can and the renaming is also required because you may want to rename a relation, because suppose you want to do a self cross product R cross R. Now, you see, in doing a self cross product, you cannot use the earlier principle, because A B cross, you have A B. Now, by qualification R dot A and R dot A, R dot B and R dot B, they do not unify, because both relations are same. So, you can change the name of the relation, call it S, then the unification has happened. Right? In this way, you can easily go around using any names. Now, naturally, like the set theory, you can compose any number of operations. Right? For example, here what we are doing is, we have relations R and S, we have done this is a Cartesian product, and then we have done a projection. I am sorry, then we have done a selection, A is equal to S. So, this is the result of the Cartesian product, and then we say this will survive, because in those A is equal to S, everything else is removed. Right? So, you can do any number of composition of operators. So, it is like just building up the algebra. Now, we get a new operation which is more specific for relational algebra. Let us say R and S are relations on schemas capital R and capital S. Right. The natural join, mind this word, the natural join, Cartesian product in general is also called join. Natural join of R and S is a relation on the schema R union S, that is, you have the attributes of R and you have the attributes of S. So, that you take every pair of tuple from instance R and every tuple from instance S, and so that is a kind of a Cartesian product. So, you are making combinations, but there is more to it. If TR and TS have the same value on each attribute in R intersection S, that is, if there is one attribute which is common between R and S, then tuples which have identical value on that attribute will only be taken in the natural join. That is not true for Cartesian product. In Cartesian product, we take all possible values, and therefore, for attributes that are in R union S, we are using the qualified name R dot A, S dot A, R dot B, S dot B. Here no. If two attributes have identical name between R and S, then you only keep those tuples which have identical value on those identical attributes. That is what it is saying. Example. So, look at these carefully. This is R, this is S. So, you know, this is capital R and this is capital S. So, R union S is A, B, C, D, E. R intersection S is B, D. Right? So, I have two identical column names B and B, D, I am sorry, D and D. Right? So, when I do the join, I have 5 records here, I have 5 records here, I should get 25 in the Cartesian product, but here no. When I pair with this tuple, any tuple here, I have to make sure that the B and D values are identical. So, I will be able to pair this with this and with this, but not with these. That is, the first record or first row on the left on R can be paired with the first row on S, because B have identical values, D have identical values. It can be paired with the third because they have identical values. It can be not be paired with anyone else. So, you have this resulting from that pairing, the next one resulting from that pairing. If you follow this all through, is what you get the natural join as. So, what will happen in natural join? R dot B and S dot B necessarily, similarly R dot D and S dot D, these two will necessarily have identical values in the columns, because that is how you are choosing 1 1 you have chosen. Similarly, let us say if you take the next one 2A, there is no 2A. So, this entire thing will not produce anything. Take the next one, you have 4B, there is no 4B here, entire thing will not have anything. Then you have this which has 1A. So, again you will have 2 of these. Then you have delta which is 2B. So, 2B will only have this 5. Now, necessarily on both these R dot B and S dot B you will have identical values, and on R dot D and S dot D will also have identical values. This is by the way you are making the choice. So, it is redundant to keep both. So, you remove one from the table, and once you remove, you do not need to call it by a qualified name. So, that is exactly how you get this table. So, in this table you do not get 2 B's or 2 D's that are identical. So, if you look at what you have done a cross product, then on identical column names R dot B and S dot B, you have checked if the values are equal on B, equal on D, inclusive, they will have to be equal on both. You have selected only those tuples. So, then you have got 7 columns of that, you have taken the distinct 3, and of the duplicate ones you have taken just 1, removing the other 2, you have 5. We will see that this is a very, very powerful operation which we will use rampantly I reiterate, across different query processing. So, you will have to practice and learn this really well. So, that was about the relational operators. Now, other than that there are some aggregate operators. So, relational operators, you will have to remember that the operators always take 1 or 2 relations. Some operators are unary, like select, like project. So, they take one relation and give you one relation. Some are binary, like union, intersection, difference, Cartesian product, natural join. They take 2 relations and give you one relation. Remember that the input will always have to be relation, the output will always be a relation. And it is possible that in some cases you might get a empty relation also, a relation which does not have any tuple. So, you will go back and say there is no answer. Now, these are the basic relational operators. Then we have a set of what is called aggregate operators. The concept of the aggregate operators is that you take a relation again, then based on one or more columns or certain conditions, you do an aggregation. So, kind of you have a table A, B, I say that I want to do an aggregation on column B. What is that aggregation? I want to make a sum. Of course, the type of that column has to be such that that particular aggregate operation is possible. So, I can do a sum on this column to get 10. I can do a max on this column to get 5, like this. You can do a aggregation on a relationally operated file also. For example, I will say that well, I want to aggregate values that are more than 2. Right. So, I will take this R and then do B greater than 2 R. What does this give me? This gives me a new relation, right, a relation which does not have this. And on this I do a sum on B to get 8. So, two main differences between the relational operators and aggregation operators. Relational operators are always dealing with certain structure, tuples and so on, and always will produce a relation. Whereas, aggregate operations will do, and typically aggregate operations are numerical, as you can see, all of these are numerical operators. They will necessarily take one or more columns, the tuples, and do some aggregation arithmetic on those, and they will produce a single value. They do not produce a table, certainly, because the sum of your budget or your maximum salary of an employee or the average execution time of a query and so on, these are the different aggregations that can happen, will not produce a multiple value. So, in aggregation input is a table and the output is a single value. So, that is how these are distinguished. Aggregation operators are not fundamental to pure relational algebra, because relational algebra only talks about relation, but these are, as we will see, will come as additional operators as we write relational algebra in the form of SQL kind of language, because they become very handy, and we will show you how to do those in time. So, that was so each query input is a table and a set of tables, and each query output is a table. Each data in the output table appears in one of the input tables. Relational algebra is not Turing complete, which means there are problems, there are programs for which no relational algebraic solution can be written, and that is one of the reasons that you will necessarily have to go with a host language. So, this is a summary. This is just for your quick reference till you get totally comfortable with these operators, which we will have to soon get comfortable with. So, in the module today, we have introduced the relational algebra with its basic operators, so on. Thank you very much for your attention, and we will continue on this in the next module. Have a nice time.